We have here a different question related to numerical approximations using Taylor polynomials. And the question now is, suppose we have the exponential and we want to evaluate exponentials with arguments which are in this interval here, right? Between -1 and 1. And what we want to do is to choose the smallest degree for the Taylor polynomial that is necessary if we want to approximate these exponentials in any point of this interval with an error which is smaller than, well, with an accuracy that is at least 3 decimal places. So the error, okay, need to be smaller than 10 to the -3. All right? This an error smaller than this guarantees that at least 3 decimal places are exact. Okay, so that is the question. And since the error of the Taylor approximation is given by the remainder, what we have to do to calculate the remainder for an arbitrary degree, right, an arbitrary n. The remainder of the exponential is easy because the nth derivative of the exponential is the exponential, okay? So what we have here, expanding around 0, which is the middle point of this interval, is that the remainder of degree n around 0 is the, well, n+1 derivative, actually, the n+1 derivative, but that's the exponential, okay? So it's the exponential but an intermediate point, so theta x, where theta is some value between 0 and 1, unknown, okay? And down here we have n+1 factorial, and here we have x to the power n+1. All right? Okay, now we need to find an upper bound of this. So let's find an upper bound. And in this upper bound, we are going to take into account that x, the absolute value of x, is smaller than or equal to 1, right? In this interval. Okay? So that means that this factor here is and finding an upper bound for this is just 1, right? So the absolute value of this is smaller than or equal to 1 if this is true, right? The denominator doesn't change, and what we need is now an upper bound for this number here. Well, of course, the upper bound, or the largest value the exponential can take if x is anywhere between this interval is clearly, since it is an increasing function, is clearly the value of the exponential at the point 1. So e is an upper bound for all the values this can take. So we have e over n+1 factorial times 1. So this is an upper bound of the remainder for any arbitrary degree. So what we need now is that this is smaller than 10 to the -3. Okay? And what we have to do is to substitute values of x so that, values of n, so that this number here is smaller than 10 to the -3 there. Okay. Well, if you start substituting values and calculating this expression, what you find is that this happens for the first time when n is equal to 6, right? 7 factorial, which is the number you have to put here, is 5040, right? And remember that this is 2.7 something, right? 6 factorial, which would correspond to n equal to 5, is 720. So almost 3 divided by 720 is larger than 10 to the -3. But 2.7 divided by 5,000 is clearly smaller than 10 to the -3. So the first value that we need to input for n in order to achieve this is 6, right? So we need the 6th order polynomial for that. So we need the to approximate the exponential by this polynomial. X squared divided by 2, x cubed divided by 6 is 4 over 24, x5 over 120, x6 over 720. Okay, this is 20. So this is the polynomial that we need to use. Obviously, Depending on the value of x, the accuracy is larger or smaller, right? The smallest accuracy will be obtained when x is farther apart from 1, right? So in particular, when x is equal to 1 is when we will get the worst accuracy. But the fact that we're taking n equal to 6, so we're approximating with this polynomial, guarantees that the error that we're making is still smaller than that. Even in the worst case, we guarantee that this is smaller than that. But if we take values of x close to 0, the accuracy will be much, much more than this. So we will get more more exact decimal places than this one. Okay?